Thank you all for coming, even though it's raining a bit this morning. Really appreciate having me today. My name is Anhong. I'm an assistant professor in computer science and engineering at University of Michigan, also affiliated with School of Information. So today I'm going to talk about some of our lab's work on building and deploying assistive technologies to make the real world more accessible for people with disabilities and towards this idea of personal accessibility through personal assistive technology. So let's start with an example first. Right? So the world is full of physical interfaces like microwaves, information kiosks, thermostats, and checkout terminals. And many objects around us are also acquiring digital interfaces, right? Even our digital electronic toothbrush, cooking pots, they all have a bit of a screen and some controls that you can use now, and they're also acquiring touchscreens. So I want to ask you to think about what kind of assumptions are these devices making? So for example, if we think about you run into this kiosk, what kind of ability assumptions are they making for you to be able to interact with it?
Probably for the user to change some parameters.
Okay, so the user needs to be able to control it in some sense? Anyone else? Yeah.
Well, with the screen, you definitely have to be able to see to get the right things.
Yeah, you'll have to be able to see. If it makes sound, you should be able to hear and understand the sound and speech. And also, it requires you to be able to lift your arm, touch the interface, and also lift precisely on the same point within a time span, right? So there are all these assumptions that are making based on this very simple user interface. So although these kind of interfaces are wonderful for some people, and they have some benefits of being more flexible, they are also increasingly incomprehensible and unusable for others due to their ability assumptions, right? So they require good vision, hearing, speech, and fine motor abilities. So we have figured out ways to make these devices accessible for specific population, right? So for example, for blind people, we have self-voicing devices like talking microwaves and clocks and scales that the user is able to interact with, and the device will read out what is being clicked. And for example, if someone is blind and also deaf, for deaf-blind people, tactile markings or braille augmentations can make these devices more accessible, so people can use their tactile sensation to understand and operate these machines. So how do we make things accessible today? Right? So physical objects can be designed to be accessible for certain people. And on the other hand, the digital information can be accessed through assistive technologies, right? So we have screen readers, we have voice controls and physical controllers, and many other types of assistive technologies. So give you an example of assistive technology. So here is screen reader, which is a commonly used assistive technology for blind people. So let me play a clip.
Drag your finger around the screen to explore.
Settings, App Store, reminders, mail, FaceTime.
This works with almost any word, feature, or app name.
So with this accessibility layer, and this works on mobile devices and also on desktop, users are able to interact with a lot of digital information, right? And another example of assistive technology for deaf and hard of hearing people is closed captions. So here I show you how closed captions work back in the day on television and also on YouTube of a video of Michael giving a talk at Michigan a couple years ago. So we currently have created accessibility and usability guidelines to help companies design products to make things accessible that are usable by more people, right? However, to make things accessible, it requires each product to follow a set of follow these guidelines, such as we have perceptible information, tolerance for error, flexibility of use. These you might have learned in universal design principles. but also we have WCAG, Web Content Accessibility Guidelines, ATAG, Authoring Tool Accessibility Guidelines, and we have, alt text for images, we have closed captions for videos and audio descriptions for videos, for audio and audio description for video. So these are all amazing tools and guidelines that we can use to make physical and digital information more accessible. However, in reality, there is still only a very small percentage of products that are actually accessible. So why? So as pointed out in a recent paper by Grant van der Heijden and co-authors, it is almost impossible to make each thing accessible using this paradigm. So the reason is that we have all of these guidelines, but the current guidelines have hundreds of individual requirements in them, requiring every single developer and company to follow each guideline to improve their products. Yet these guidelines still does not cover all the people with all kinds of types, degrees, and combinations of disabilities. And so essentially requiring each product team and company to make their own product accessible for all people is not going to work. And I will add that anything, especially the devices that I showed you, anything physically situated in the real world, like the kiosk that's already there, like the microwave that's already put into a kitchen, they have to make assumptions about the user, and it's fixed, right? So think about the chair you're sitting on. That chair is not uniquely designed for you. So even though you can sit in it, it's not the most comfortable for you. It's designed to work with maybe 95% of the population, but it doesn't work with your needs the best. So anything physically situated is often fixed and have to make assumptions about the user. And even though, let's say, you can add like screen readers and assistive touch and all these assistive technology on like a cooking pot or anything with a display, that is also not going to work because, first of all, the cost consideration, the requirement of hardware and software, maybe the limited screen state for you to perform interactions. But also, if you are familiar with assistive technology, you know that people make deep customizations on their assistive tools, right? So they customize the gestures, the settings for themselves. So there is no way for you to be able to interact with something that's in the real world and be able to have it adapt to your needs directly in the most deep personalized way. So to address this, one framework is ability-based design. Some of you might be familiar with this. So ability-based design is, the goal is to design things to accommodate the user's ability. So the system that we call a ability-based system can adapt based on the user, right? So in some sense, the current digital accessibility ecosystem is kind of already designed in this way. But breaking this down, I think ability-based systems have really two parts. One part is the physical and digital objects to be accessed. And the other part is the assistive technology layer that work with those information to present them to the user. So I think in the context of digital objects, such as mobile, web, this makes sense, right? So you can surface the information in one way and the user is able to use their own assistive technology to work with it. But if it is accessing the real world, this often fails because the physical infrastructure is often rigid and cannot adapt. So our lab have been working towards this, this vision of personal assistive technology. So I draw from a mainframe computing where often many users access the same one device. And we transformed from that to personal computing, where it really enabled users to consume, create, and innovate by themselves. And mapping this to personal assistive technology, the idea is personal assistive technology aims to empower people with disabilities to be able to access the physical and digital world in their own terms using their preferred devices and modalities, and be able to leverage their domain expertise to create and customize technology for themselves. So I'm going to show you a couple projects that kind of map to how we think about this So using the same illustration, now we are kind of moving this assistive technology part closer to the user. And thus it becomes personal, more personal, allowing it to access the rigid physical and digital objects out there that's already in the real world. So I'm going to show you a few examples of how personal assistive technology will be able to let people use their own devices and modalities and augment their environments, as well as enable people with disability to make their own assistive technology and leverage broader context. So I will start with the first ones. So going back to this example, making all of these interfaces accessible has been a long-standing challenge. And especially because there's already a huge legacy problem of these devices already in the real world, right? They are not connected to the internet, and the user is not able to control them using a different device. So in our prior work, we have developed systems to interpret these interfaces, either static or dynamic, and enabling blind people to independently access them. So to show you, similar
Settings,
to
App Store, reminders, mail.
So similar to how the
FaceTime.
iOS screen reader work, the user is able to move their finger on the digital interface to hear what is underneath their finger. We kind of map that experience to the physical interface.
Kitchen timer. Kitchen timer and 2. 2. 2 and 5. 5. 5 and 2. 2 and 5. 2 and 1. 1 and 2. 1 and 2. 2.
So as you can see, when the user moves their finger on the physical interface, the system VisLens will be able to provide real-time feedback of what is underneath the user's fingers, kind of map to how a screen reader works for digital information. So here is also show you a range of interfaces that this approach can work on. But the idea here is that we're able to bring the amazing affordances of digital accessibility into the real world. And we're able to allow the user to use their own device and their own preferred modality to access such information. So think about if this user prefer a faster speech, or this person prefer tactile feedback, or this person may use a different assist technology to get the output. They are able to transform what is in the real world, what is the information that they need to access in the physical environment, into this preferred modality. And this device, this smartphone they have, is really know them the best, right? Have all the context and understanding about the user's abilities and preferences. So about 2 years ago, in summer 2023, we deployed this app on the iOS App Store and have had about 500 people use this for 1,000 different interfaces. And then subsequently, maybe coincidentally, Apple added a feature in iOS accessibility settings. Okay, so you got the idea that the user is able to use similar interaction, although it still doesn't read what is under your finger. You kind of have to show what is first above your finger and then know how much to move up to activate it. Right? So building on VisLens, we then develop a series of extensions to extend the capability of what kind of interfaces and in what modality the user can access. Right? So first, we developed this extension called Facade, which enable blind people to create these 3D printed tactile overlays for their inaccessible appliances. Right? So they can take a picture of this interface with a reference image, like a dollar bill or a credit card that you know the absolute dimension and features. Then you can use this to retrieve the button information and be able to generate a 3D printed overlay that the user can then retrofit and augment their appliance. So this lets people augment their own environments using this approach. And furthermore, we also extended this to work with more dynamic touchscreens. What we did is we used kind of the videos that people interact with this machine. Maybe like you used a coffee maker to order latte, and somebody else go in and really change the settings. And gradually we can collect those videos and be able to reverse engineer this state machine of how this machine works. And we're able to present this using an audio interface to a blind user so that they can specify like which, what operations they want. And then the system is able to guide them to complete that task step by step. And more recently, we developed a phone case extension that we call brush lens that allow both blind users and also motor impaired people with difficulty with fine motor control to be able to access touchscreen kiosk. So the problem we're trying to solve here is that in the previous extension that the blind user is able to use the touchscreen using the system, the users still have to be really precise in moving their finger following this audio guidance. And we found that sometimes cause challenges because that, if the UI is kind of particularly cluttered, the user may make mistakes and it might take a lot of back and forth. So the problem we're trying to solve is, okay, how about we can use a hardware interaction proxy to automatically perform the actuation for the user so that the user can just focus on broad stroke, like, brushing on this interface without worrying about the very fine motor control. And then the system you can delegate to the system to perform the precise actuation. So let me play this clip.
We present brushless, a hardware interaction proxy to make touchscreen devices more accessible for people with diverse abilities. Brushless uses multiple actuators to touch the screen. It automatically determines when to activate the actuator and precisely touch the screen on behalf of the user. We show the brushless with solenoid and auto-clicker actuators. Visually or motor impaired users can use the brushless accessible interface on their smartphones to explore and interact with inaccessible touchscreens.
So in this case, we build two different phone cases. One is with mechanical actuators that can work with physical buttons, capacitive or conductive screens. And then the other with these auto clickers that you can actually see that is often used in mobile farms. Right? So people like in mobile farms, you have like smartphones like running a TikTok video, and then you have this connected to a auto clicker and automatically like a bunch of videos. So these automated methods. So we bought a bunch of those and we built the phone case to be able to change the capacitance dynamically. And then when the user is brushing on the screen, it's able to just provide the touch at the right moment for the user. So the idea here is that if you see that there are two different modes, right? So one mode that's supporting blind users is able to map the functions that the user is trying to perform onto an interface that they can use voiceover to control. On the other mode, to support people with that lack fine motor control, we're able to create a custom interface that magnify the buttons that's close to where the phone is, so it make it easier for the user to activate it. So in this approach, if you think about how this brings that interface closer, this assistive technology closer to the user, is like this interface can really know what the user needs, right? Whether they need motor support or visual support or other kinds of support, and be able to translate whatever the user's ability and perform interactions that's kind of assumed by that physical object, or in this case, the touchscreen out there. So this line of work on kind of providing assistance for dynamic physical interfaces can also be very broadly be extended to augment how people generally interact with touchscreens in the real world, right? So for example, when configuring complicated medical devices or when interacting with machines in a different language, these guidance can also be provided through a augmented reality overlay, right? It doesn't need to be audio or haptics by itself. So these overlays can be in the form of visual indicators, animated instructions, or interface simplifications. So we also kind of explore some authoring tools to create interactive AR tutorials through narration and demonstration. So in this case, like using the same sort of backbone of how we model the interface structure, we're able to provide kind of a step-by-step tutorial to guide the user to perform operations on this printer. Okay, so any questions so far? Yeah.
What is the class of people with motor challenges that can't use a touchscreen but still could hold the phone consistently enough to be able to swipe it over like a touchscreen?
I would say it doesn't map to a particular condition, but we recruited participants who are able to, for example, rest their arm on the screen, and they are able to move their hand around, even though it's not in a smooth kind of zigzag motion, but it reduces the error rate a lot, and the users are able to complete the task using this kind of augmentation. Yeah.
I've got a question.
Yeah.
So you motivated with sort of the personal computer, and one of the weird ironies is that the personal computer wasn't very personal. It was very generic. It was just cheap enough that everyone could get one. But I feel like your pitch here is about essentially mass customization a little bit more. Is that fair?
Yes. I think with the personal computer, the kind of analogy I'm also drawing is you can access the same content on the web by using many very different extensions. Yeah. Right, so you can change your contrast. You can have it read out at the same time. You can, use dark mode or light mode, like many other extensions that you have on your browser or on your computer. So you can have these deep customizations that really work for you. And this is a device that's personal to you. And then you can use this to access the vast amount of information out there.
So I can install stuff on it, basically.
Yeah.
You also mentioned the microwave overlay. Was the idea to take a picture and then ship it out to some third party and then receive it, or was the person supposed to navigate on their own?
Yeah, that's a great question. So when we did the project, I think digital fabrication is in parallel advancing. And I think the vision is that a blind user may not have a printer at home, but they may, in the future, have a 3D printer at home. But there are a lot of accessibility challenges in how to configure that, how to remove the support material and all that. But when we reach there, this is something that the user can do completely by themselves or with a caregiver at home. But for some of these devices, we print them in the lab, or we use like a service like 3D Hubs, and then we are able to. The video actually you saw is when they are about to print your object, they will send you a link, and you can watch the live stream of how it's being printed. It's pretty cool. Yeah.
I really like the idea of sort of thinking about sort of changing the product and making it more accessible versus these personal devices. And I was wondering if there are opportunities or ways to think about kind of approaches that are hybrid or meeting both ways, like perhaps the product provides some set of like metadata that makes the personal device makes it easier for the personal device to still retain customizability, but gain the types of sort of underlying digital information or like assumptions about the product that enables it to maybe do more. Or
So that's a great point. So eventually, for this whole ecosystem to work, to make all, let's say, 99% of the devices or information accessible, it requires a collaboration between all of these terms. But for example, each individual company who is serving this information, they don't have to become that. So this is pointed out by Grant Vanderheiden's paper. It's like they don't have to have a dedicated accessibility team to make it accessible for every single population, but they can just serve this information in the right way that can be consumed by this information bot. So that's what they say. So the kind of structure that they propose is there is this info bot and there is this UI generator, right? So with these two in combination, then you are able to kind of pair them to work well. Yeah. Okay, so let's move on. So I've just shown you a few examples of how we empower people with disabilities to be able to access physical information using their preferred device and modality. So next, I want to ask you, so these assistive technologies, who developed them? Who designed them? Apple, Google, companies, and maybe individual researchers and product teams, right? So they are developed by designers, developers, and researchers. And in practice, these technologies are typically designed for common use cases in order to maximize their broad applicability, right? Just like your chair, right? So it's trying to fit a majority of the population. But with this goal, right, to maximize broad applicability, the consequence is that they become one size fits all and often inflexible, and oftentimes they are falling short of supporting the unique needs and preferences of end users. So the end users is not able to make changes to these technologies to really make it work for themselves. So we conducted a series of qualitative studies with blind participants to understand what are the situations that there are these breakdowns, and how do blind people want to customize or create new solutions. And so we found that people are already putting in a significant efforts to create workarounds to try to adapt to these long tail of needs. But existing workarounds are often very tedious, overwhelming, and ineffective, right? Okay, so to illustrate this, I will walk through one example given by our participant where they want to use the AI application Seeing AI developed by Microsoft to sort mail. So what they do is they pull up this phone, this app using the short text mode, and then they aim the camera to scan this envelope, right? So they want to figure out, okay, are these mail for me or for my family or for others, right? And so when they do this scanning, instead of just reading out the information that's relevant for them, which is in this case just their name, they get all of the they get frustrated by all the information that the app will provide. And oftentimes, because of camera aiming issues, it will kind of repeat over and over again, and they were not able to complete this task. So in response, this participant imagined being able to kind of create an assistive technology on top of Seeing AI that's just able to tell them this information that they want, which is their name, right? And this is just one example of how like a blind participant is engaged in this design process, this ideation process. And so we observed in this study a range of breakdowns and strategies that people have been using, right? So for example, they want to find just their name or address, just the expiration date of the product, or just the number of an incoming bus. So there is actually a huge variety of things that people want to filter, and that they are not able to do with the kind of general purpose OCR or text reading applications today. And also, blind people often have to switch between multiple services to achieve one goal. Like for example, when one of our participants was sorting mail using in different languages, some are in English, some in Arabic. So they have this kind of trick of using Seeing AI to read the mail if it is English, or use Envision AI if it is in Arabic. So they know like this kind of work well in that situation. So they have to kind of manually do this, right? So they use one, they figure out what language it is, and then they switch to the other app, right? Or in another case, when a blind user is getting a scene description from a generative AI service such as Be My AI powered by GPT-4o, they have very detailed strategies of dealing with these potential AI errors. Like in high-stakes situations, they will cross-check with other AI services like cloud, or sometimes fall back to human assistance. And they also kind of often layer multiple services, right? So for example, when blind people are navigating unfamiliar spaces, they will use a combination of multiple applications such as Google Maps to get directions, Blind Square to know more about the landmarks, and also OKO to kind of specifically cross sidewalks, right? So the user is already doing this kind of manual process of switching and combining different applications and different services together. So from cases like this, as well as from prior work, we know that blind people, in this case, they are really the domain experts in envisioning, designing, and hacking assistive technology. But because of the current limitations in this design and hacking process, individual needs often become unaddressed. So our goal is to imagine how can we empower blind people to leverage their expertise and creativity to be able to create custom mobile assistive technology to address these needs. So instead of they have to channel these needs to a developer or a company, and then the companies create something that can work with a range of needs. What if we can give the tools to the people and they can create their own solutions? Right? So that's what we're imagining. So we are going beyond consumption, but also to creation. And personal assistive technology here also aims to empower people to leverage their expertise to be able to create technologies for themselves, right? So essentially, this part, they can change it, and they can create this themselves. So going back to Michael's question, now not only they can install things, maybe they can make those extensions and program those extensions. So end-user programming is a method that supports non-professionals to create software artifacts to be able to achieve their goals in their own domains of expertise. It's potentially suitable for this goal that we're talking about, but it is critical to address the challenges to make them make these end-user creation processes and tools approachable, accessible, and expressive enough for blind people. Right? So the traditional paradigm of end-user programming is often too high of a barrier for blind people to be able to create assistive technology. So we need to figure out where's the right abstraction. So that's what we investigated in our recent work, so that blind people could create filters such as find my name on envelope to just filter their name, or in the case of sorting grocery, they can create something like find date on grocery item. So let me show you, once this program is created, how does it work?
Runs the program. Pause running. Button. No date found on grocery product. Found date, January 10th, 2024. Brown. Found date, January 10th, 2024. Yellow-orange.
So the user is able to run this program called find date on grocery item, and then aim at the packages or the grocery that they have and be able to turn around and hear this live update of just the right information they want. So to develop this application, we have 3 design goals, right? So we want to make it expressive, right? What that means is it should be able to support a wide range of needs, and also should be able to easily extend it into more models and tasks in the future. And second is to make it approachable, which means that for blind people who have very limited or no programming experience, it should be understandable to them, and they still provide easy entry points for them to be able to create and make changes. And finally is accessibility, which means that on the one hand, it should be accessible to screen readers so blind people can use them. But on the other hand, it should also provide sufficient contextual information that help people understand what's going on. So even when the object they're trying to find is not in the field of view, it should still provide surrounding context to help them aim the camera and eventually get the task done. So in order to make it expressive, we kind of used all the scenarios that apply in this case in the previous qualitative study, and we derived this program representation to support this kind of visual information filter task. So this program followed this pattern of find something on something, and each thing can have adjectives on it that can denote color, location, or size, or other attributes. So with this very simple structure, find something on something, people are able to create assistive programs to find the number on the bus, to find the largest text on a poster, or find the address on an envelope, right? And this can also be easily extended in the future to support new models and object classes, as well as maybe alternative terms of find or on.
Drop downs, are those pre-populated, or is that a closed vocabulary, like license plate? Was that built in, or is that something that end user offered?
Yeah, I will show you that.
Okay.
But those will depend on kind of the models that you plug in. For example, if you use YOLO, it will give you a set of object classes, and the user can choose from that. Or if you use a combination of different models, then you can have a more variety. Or if you use a VLM, then it's more flexible in that case. Yeah. So when running the filtering programs, the ProgramAlly application will iteratively find the items and then provide the information to the user. And when the target object or maybe the number is not found, but the bus is found, it will also provide contextual information to help the user know like what is happening right now. And maybe they see that grocery item, but then they keep turning to find the expiration date, right? And one kind of side effect we found in our study is that this actually may reduce the hallucination from VLM models. So if you just ask the model like a question, then sometimes it's able to tell you something that's not part of this image. But using this more structured filtering approach, plug this into a vision language model, it's actually be able to kind of reason better about, okay, this is what I see, and that's the number that's within this bus, not the number that's somewhere else, maybe on a different vehicle. Yeah, so we'll find the bus and then find the numbers, and it will read these things to the user, and the user can make changes. So in order to support approachability and accessibility, so how do we support the user be able to create these applications, is we develop a set of multimodal end user programming interfaces. So there are block-based programming, there is natural language programming, and there is programming by example. So in the block mode, users can create the program just by using like drop down, like similar to how you may configure like a iOS shortcut or a IFTTT if this then that programs. So this gives you like sort of the most control and most precision, but it will take a bit longer because you have to navigate through all of these interfaces, right? And then in the second question mode, the user can just speak their question. Oh, I want to find number on the bus. I want to know like what is my name? Like, is this male for me, right? And then we can use fine tuning and be able to generate candidate programs for the user, and then they can continue to edit it and use them if they want. And the third mode is explore mode. So this mode kind of takes inspiration from programming by example. So the user can kind of first aim the camera at the scene or this object and get a bunch of output. And then once they hear something that they want, they can later go back and select that item 73 that okay, I know that's the bus number, so I want to create this program related to this. Then it's able to generate a program using the tree representation of the scene and be able to kind of go back and generate this program. And then it will become find number on bus. So these are kind of the three different user creation methods that we created. So we then conducted a user study with 12 blind participants to see like whether this approach really work and be able to support accessibility use cases that were not possible before, and what are the preferences and trade-offs of people using these three different creation methods, right? So what we found is that each of these creation interfaces actually have their own strengths and challenges. So for block mode, although it takes more time, it's generally a bit more time consuming, participants appreciate that it was very precise and give them the control over the final program. Especially useful, this mode is especially useful when they have something in mind that they want to create. And for question mode, participants found it to be very intuitive, right? You just speak what you want, and then it's able to kind of potentially help you generate the programs that can match the user's goal. Although sometimes the output was not what they intended, and it might take more back and forth for the user. So I think this is not the ultimate form of how the natural language mode should look like, but I think there's more work to be done to kind of how you transition between these multiple different ways of creating this program to be able to best match the user's intent. And then third, for the explore mode, participants found that it is particularly helpful for situations of unknown. Right? So they aim the camera, they may discover something they didn't know before or some attribute that they didn't think about, and they're able to use those in the programs to make it serve their needs. So what this means is that providing these options, a combination of multiple options to users is kind of important to make this user programming possible and approachable for users with a range of use cases and abilities. So as participant 4 put it, it's all contextual. It depends on what you want to do. I would use different methods based on what I know about the environment. If you already have an image you're working with, for example, you want to explore it, then that's what you will use. It really depends on the situation. So so provide, again, this kind of highlights that you need to provide multiple different modalities and ways for the user to be able to create an author that may best suit their kind of technical background or what they're trying to do in situ. And finally, participants see the benefit of using this approach, and I think I really like this quote that says, "It all comes down to providing choice. Ultimately, you're putting the information available in the person's hands to choose. It is creating modularity to access the information." I wish more creators or assistive technology companies thought about how can we take these pieces of information and put it in the hands of the people who need it so that they can then modify it and change it and make it their own. So going back to kind of these different strategies and breakdowns that we identified in the qualitative study, kind of ProgramAlly, the tool that I just showed you, kind of support this first gap of general purpose recognizers does not support the specific use cases. But looking into the future, there are a lot of opportunities in kind of supporting the other breakdowns and strategies as well. So for example, people automatically switch between multiple services, or people layer multiple applications together. How can we allow people to be able to author these workarounds in the operating system level that's able to combine these information together? So for example, some of our ongoing explorations look into how can we build snippets of assistive technology extensions that can work on top of the existing commercial ecosystem. So there might be one thing that the user needs on top of Be My AI that's to better aim their camera. Then we can use that the shortcut automation to be able to quickly kind of help the user achieve that task and bring them back to the application they're already using. Okay, any questions at this point? Okay, so I share with you other than kind of how we can personal assistive technology can support users to use their own devices, modalities, and augment their own environment. So this last example kind of help illustrate how we can enable people with disability to be able to make their own AI assistive software. And and there are a lot of potential avenues. So for example, to kind of broaden this towards more people, maybe we can have people create, there are different communities that can create, and they'll be able to share solutions and reuse, and we'll be able to develop templates. And maybe we can create a community for people to be able to kind of tap into this knowledge source and enable a community of knowledge sharing. And one thing that I touched on briefly is kind of intent, right? So many of these programming methods aim at kind of capturing what the user wants to do, right? And help them kind of externalize that in the most natural way, whether it's natural language or is, programming by example or is direct creation, right? So in our recent work, we also explored this in a project called WorldScribe to leverage their broader context. So WorldScribe is a project that we developed a system that can generate live visual descriptions that are adaptive to the user's intent, movement, and also visual and auditory context. So what you see here is as the user is moving around, right? If they are turning very quickly, or if they're walking quickly, or the visual scene is changing very quickly, then we will provide bits and snippets of information. And then the user kind of start to focus on a certain object or a certain scene in front of them, then more details will be provided to the user, right? Because if you think about the current way of using GPT-4 or Be My AI to get image description, it essentially just is not aware of what the user is doing and is providing very long description. So when people use these assistive tools, they often have to stop and ask questions and use this turn-by-turn interaction to perform to their task. But here in WorldScribe, we're trying to map the description to the user's context, right? So the user can specify their intent, and then based on how dynamic the environment is or their movement, so we kind of map the description's granularity or length to kind of what they're doing in the moment. And also, we can manipulate the presentation of the description. So for example, if music starts playing or the environment become more noisy, then we can raise the volume of the description to make it easier to hear. Or if someone starts talking to them and have a conversation, then we can pause the description and without disrupting what is happening, what the user might be doing. That's more important. So overall, that's kind of, I give you a bunch of examples of personal assistive technology. And as we are moving assistive technology closer to the user and becomes more personal and enable them to create and modify and use their preferred devices, etc., I believe it will move us towards a more accessible future that can be deeply personalized, right? But I also want to take a step back because I believe this approach might be able to make it both deeply personalized and also more broadly universal. And accessibility ultimately benefits everyone. So I just want to provide a few examples of how I think these approaches might be able to generalize beyond people who are blind and also people with disabilities. So for example, the multimodal task guidance systems like VisLens and BrushLens, as I showed you a couple examples earlier, might be able to make interfaces more usable and easier to use for more people, for everyone. And my lab have been starting to work on projects related to kind of task guidance in the medical domain. And there's a lot of kind of commonality there, as in the users, the surgeons or the medical professionals are often hands busy, eyes busy, and are very high cognitive load. And also in some of our prior work, we have looked into like in the industrial setting of supporting warehouse workers to do order picking. So many of these kind of multimodal task guidance systems may have implications beyond accessibility, but into other domains. And end user assistive tools like the ProgramAlly that I showed you may generally make creating end user workflows lower that barrier of doing that, and like by leveraging multiple modalities. So for example, I think there is some ongoing work in the deaf and hard of hearing space. So for example, what if deaf people are able to use different sound models, like to be able to construct their own kind of sound understanding software more easily. So the commonality here, I believe, is we're able to better leverage people's ability and expertise in situ and empower them to be able to create and consume with greater agency. And then we can morph that interaction experience accordingly by providing more dynamic adaptations. So all of this work will not be possible without the amazing students I've worked with. And also beyond what I shared today, there are also many other directions that I didn't cover, and I would love to potentially talk to you offline. So now I'm open for questions.
All right, we got about 10 minutes so we can have discussion.
Yeah.
Thank you so much for the presentation, and I think these are really valuable technology, especially in health. I think my question is more on how would you imagine the adaptation would work for people who are used to their normal style of living for a very long time, but now when we introduce them to this kind of new technology, and especially those they might not be used to before, and especially programming new tools, would it be too demanding for some of them, and how do you support them in the kind of adaptation process?
Mm-hmm. Yeah, so that's a great question. So for example, for the ProgramAlly work, the goal is that the user is able to author that once and be able to use it for many other repetitive situations or kind of time-sensitive situations. And or perhaps we can leverage the broader community and crowdsource these solutions so they don't even need to create those very specific ones, right? But what we found in the qualitative study is that people are already doing this workarounds every single time. So if we give them this tool, they will be able to kind of create something that can kind of be a better solution than that workaround they're already using, which could become a better solution. But I think we'd love to deploy that out in the real world and be able to collect data and see whether people will be able to use it in the ways that we kind of identified here. Yeah. Yeah.
Thank you for the great talk. I noticed that in the first 3 projects, people were using the phone to point at something, and so they at least needed the ability to be able to aim at something and point it. But in the last one, it was a head-mounted or body-mounted camera. I'm curious about your thoughts on the hardware for like the weight of the phone, do people prefer to point it at things, and also are there small systems available that people can just attach?
Yeah, so about the form factor and the device. So I think ultimately I imagine so when we did the original Vislance projects, actually we experimented with running it on the Google Glass. And back then the hardware was not good enough and it overheats very quickly, and there is no talkback or there's no screen reader on the Google Glass, even though it's running Android. So then we kind of fall back to using like a device, a smartphone that many people have, and we chose iOS because iOS is the preferred smartphone that blind people use. But I don't think that is like the only choice. So in the last one, actually, so for this live visual description, you can also use a phone perhaps or a wearable camera. But I think as wearable camera, like wearable glasses that with basically cameras, speakers, and processing power become increasingly available and more powerful, I think that would be a great form factor to support many of these. Yeah.
What is one that's widely and easily available right now that people like to use?
Yeah, so Meta Ray-Ban is a very promising option, and I think they are partnering with Be My Eyes, if I remember correctly, and also Aira. But there's they don't have open API yet for the video streaming mode. But I've seen people create hacks and workarounds, as in they create a kind of a live streaming session through Instagram or WhatsApp, and they will be able to intercept that audio feed and process it and give back the audio. So people are figuring out creative ways to do that. But one day it will be open, hopefully, and then we'll be able to create many assist technologies on top of that. Yeah.
You said that I've used a lot of technologies in my life, but like monetization, what is it the monetization for a product like this? Just to make sure it's affordable but has enough funding that it can get maintenance and develop correctly.
Mm-hmm. Mm-hmm. Yeah, so you're asking about maybe the business model of how to make these sustainable. Yeah, so I think the example of Vislance, I think is perhaps a good outcome. So we developed the initial prototypes, and then we deployed it, and there were a lot of discussions on like online forums such as the Apple Viz of people discussing how to use it, etc. And Apple eventually built it in to their operating system to support, it still only works with devices with LiDARs, but that's a big step forward, and people will be able to use it for free. So I think that's perhaps a good model. But even when we put these apps out there, we make them free and to help more people rather than trying to sell it. Yeah.
For sort of work in understanding kind of personalization in context, I was wondering if there are any sort of methodological approaches that you've seen yourself kind of gravitating towards for understanding these types of considerations.
So I'd love to talk to you more about that. I think end-user programming has a rich body of literature looking into how to make it high ceiling, low floor, and wide walls to enable that. So there's a lot of commonality, although kind of making that work for people with disabilities, like, for example, thinking about blind people trying to create visual assistive technologies without being able to see the output, right? So there's another kind of verification feedback loop that's missing. So how do we support that? I think there are interesting challenges there. Yeah.
Some ways in reference to that last comment, I'm curious, especially on like ProgramAlly, if there were like, if you saw debugging basically, and if so, how that worked. Like, I'm not sure if people were creating kind of like programs that were complex enough to have really complicated debugging, but I'm imagining like if you're using a screen reader, like debugging is probably harder because that's like kind of linear information processing, whereas visuals.
Yeah. So in the paper, we did describe a bit more of, so we do see debugging or even cross-check and using the context they already have to validate their understanding. And we think like there are opportunities, for example, like maybe combining that with WorldScribe, right? So you have this live camera feed and you'll be able to author this program, and then you can run it, and there's a laptop, so you can use that to see like whether your program is doing the right thing as you expected, and use that way. And there might be other ways to use maybe like generating a simulated environment for the user, kind of using AR to tap into that spatial understanding. So I think there are some interesting approaches there to explore.
I'm curious to what extent you think the gaps that remain are underlying sort of perceptual gaps in the models, like the model just cannot, say, recognize what is needed for many of these tasks, and we have to wait for them to get to that point. Or to what extent it is essentially about sort of filtering and shaping. Like what I took away from sort of the World Dream work was at some level that I was like, it was just tuned to produce the wrong kind of output in many cases. And that if we just did the simple step in some sense of fine tuning it for what people actually need, we can get much better. I'm curious where you see the big blocker. Is it like actually still at the perceptual level, or is it something on sort of how that's being synthesized and presented?
I think in general cases, like maybe in 90+% of the cases, I think the perceptual model, the model capability is already there, but there's a gap between what the model is capable of and how the user is able to use that for something that they care about, right? Like whether it's turn by turn or whether, so the current interaction modality has been this like turn-by-turn approach. I ask a question, I get a response. Even maybe in the advanced advanced voice with video mode, it gets pretty good, but it's still like a Q&A kind of turn back and forth approach.
That's kind of an optimistic take. Not that you're not calibrated. That's a good thing. Yeah. That suggests that through design, application programming, and so on, we could actually cross that gap. Whereas if the perceptual layer is just like not capable of it, then I think we're in trouble.
Yeah. I think now the perceptual stuff is there, and we can catch up by providing these tools and better match the, basically better kind of leverage the AI capability for HCI use cases. But once we get there, we might see like, there are further gaps in either places, and then we can iteratively improve both sides. Yeah.
One other question I was chewing on throughout the talk. On the sort of DIY end user programming side, one of the things that you know as well as I is that people tend not to customize stuff. Do you feel like there's opportunities here to break through that barrier where before it's been very challenging? Like no one changes any of the settings in Microsoft Word or any of these things, but like for this vision to come true, we need to help people feel empowered to shape those tools. How do we cross that gap?
Yeah,
maybe more of an affective gap than or than anything sort of about the tech per se.
Yeah. So I think if there will be a breakthrough, I would be optimistic that it will happen in the accessibility space first, because people with disabilities are often at the forefront, at adopting AI technologies early on. So this is an article written by Jeff Bigham and Patrick Carrington back in HCIC. So the idea is, before the technology is perfect, people are able to use it to enable something like they are not able to do before, maybe from 0 to not possible to maybe 60, 70%. But only when that technology, such as speech recognition, become 95, 99% accurate, then the mass the mass public will be able to adopt that. So really by building assistive technologies that working with people with disabilities, you are able to first provide technology enablers to improve their lives. But at the same time, you'll be able to really get into the deep human aspects of how to design these technologies for everyone. So I think that's how I see like accessibility benefits everyone in that case. Yeah.
All right. Let's thank our speaker.